In this video, we are going to look at arc length as an application of definite integral. The arc length, the length of a curve is found by summing small segments using distance formula. So if we think about very small delta x and delta y, infinitesimally small distance delta x delta y, and use Pythagorean theorem, we can estimate the curved distance by using the hypotenuse of the right triangle here. So if we use the distance formula, then distance d is equal to square root of delta x squared plus delta y squared. Or we can say the hypotenuse is square root of the leg squared plus leg squared. And now I'm just multiplying with the 1 squared because delta x over delta x is 1. We are isolating the delta x squared from the second fraction now. So I isolated the delta x squared and pulled 1 delta x in the denominator of delta y. Just a little manipulation there. And we can also factor out the delta x squared, and inside we are left with 1 plus delta y over delta x squared. So the distance d turns out to be square root 1 plus delta y over delta x squared, delta x. This delta x is squared. It can be pulled out of the square root and it would have no square next to it, no square on it. Okay, so the distance d, we know f prime of x, derivative at a point, is the instantaneous rate of change in y over change in x, which is delta y over delta x. Derivative f prime of x in terms of differentials is delta y over delta x. So we can replace delta y over delta x with f prime of x and integrate all the little small distances from the point A to point B, and we would have length of our curve. Okay, from point A to point B, square root integral of a to b square root 1 plus f prime of x squared dx. Now it's really important to remember arc length when y is a function of x. When y is a function of x, our bounds will be, the integration bounds will be the x values, and we would have square root of 1 plus f prime of x squared as an integrand. Dx is the operator. When x is a function of y, then my bounds will be the y values, and instead of f prime of x, it would be dx over dy squared, and dy would be the operator. We would have to use implicit differentiation for this one. Okay, for first two parts, I'm only going to set up the integral just so that we get hang of how to set up the integrals. So for part A, or number 1 and number 2, I'm only going to set up the integral. Okay, so how do you set up the integral? Y is equal to x squared, or we can say f of x is x squared, doesn't really matter. Y and f of x is the same thing, and f prime of x would be 2x, and arc length formula, we need to remember here we have y as a function of x equals a to x equals b, square root 1 plus f prime of x squared dx. Okay, x equals a, we are going between negative 1 to 1. If you see the graph of this function, y is equal to x squared. Between negative 1 and 1, I am looking at this length, okay, length of this curve. All right, between negative 1 to 1, square root 1 plus f prime of x is 2x. So 2x squared dx. All right, and that's just the integral setup for the arc length for the given curve over the interval negative 1 to 1. Another example, again, we're only going to focus on setting up the integral. So y is 3 over 2, x to the power 2/3. Y prime is 3 over 2 times 2 over 3, x to the power 2/3 minus 1. Y prime comes out to be x to the power 2/3 minus 1, which is negative 1/3. So this is my y prime. Again, the arc length, we are given y as a function of x, so arc length is going to equal x equals a to b. Notice I did not graph this function because graphing is not necessary for writing the formula for arc length or for finding the arc length. There's no need to graph. Okay, so square root of 1 plus f prime of x, which is negative 1/3 squared dx. All right, which is 1 to 8 square root 1 plus x to the power negative 2/3 dx. Okay, and that's the integral setup for the arc length. Next few problems we will work out and find the solutions all the way to the end. So here we are. Find the arc length of graph of y equals x cubed plus 6 plus 1 over 2x on the interval 1/2 to 2. So we're going from this interval 1/2 to 2, and we are looking at this arc length. It's not a straight line. We cannot measure with the ruler, so we are using calculus to find the length of that arc. So first of all, my formula for arc length, remember, we are given y as a function of x. So arc length is x equals a to x equals b square root 1 plus f prime of x squared dx. So here I'm given the y. Let's go ahead and find the y prime, which is f prime of x. It turns out to be 1/6 times 3x squared minus 2 times x to the power negative 2, which turns out to be x squared over 2 minus, it would be 1/2 here. Okay, yes, it would be 1/2, not the 2, so 1/2 minus 1 over 2x squared. So this is my derivative, f prime of x, or y prime. Okay, let's go ahead and plug it into the formula. So arc length turns out to be x equals a. We're looking between 1/2 to 2 square root 1 plus y prime squared, which is x squared over 2 minus 1 over 2x squared dx. Okay, let us simplify this. So from 1/2 to 2, I'm going to open the bag. I'm going to FOIL this parentheses. 1 plus x squared over 4. 1 plus x squared over 4 plus 1 over x to the 1 over 4. It would be x to the 4th, right? Okay, it would be x to the 4th, not x squared. So let's FOIL it one more time. So 1 plus x to the 4th over 4 plus 1 over 4x to the 4th minus 2 times x squared, 2 times x squared over 2 times 1/2 x squared dx. Okay, let's see what does that turn out to be now. If there's anything I can cancel. Looks like I can cancel the x squared and x squared and one of the 2's as well. So what I'm left with is 1/2 to 2 square root 1 plus x to the 4th over 4 plus 1 over 4x to the 4th, and then minus half dx. Now, looks like there are some like terms here. We do have the like terms as negative 1/2 and positive 1. So 1/2 to 2 square root 1 minus half is positive 1/2. So positive 1/2 plus 1 over 4 x to the 4th dx. I'm going to pull out a 1/4 from the square root. If I get a 1/4 out of the square root, I would actually have 1/2 out in the front. So inside it would be x to the 4th plus 2 plus 1 over x to the 4th dx. Again, 1/2 got pulled out of the square root, half to 2, and the inside looks like it's x squared plus 1 over x squared to the square dx. finally, we can get rid of the square and the square root, and my integral turns out to be 1/2 to 2 x squared plus, I'm going to write it as x to the power -2 just because it's easier to look at it when we are integrating. So we are left with 1/2. We can just integrate the pieces. 1/2 x to the power 3/3 plus x to the power -2 plus 1 is -1 divided by -1, and the bounds are from 1/2 to 2. And let's see, what does it turn out to be when I plug in the bounds? X cubed over 3 minus 1 over x, 1/2 x cubed over 3 minus 1 over x, 1/2 to 2. That would turn out to be, plug in the upper bound and the lower bound. It's going to be 1/2 2 to the third over 3 minus 1 over 2 minus 1/2 to the third over 3 plus 1 over 1/2. This is going to equal, when you simplify the integral, it's going to come out to be 33 over 16. Okay. You can use a calculator or just simplify these fractions. All right, next example. Here we are. Find the arc length of graph of this function. Okay, so here, notice we're not given y as a function of x. Instead, we're given this function in the implicit form. So I'm going to try to express it as y as a function of x or x as a function of y. I see it's easier to express it as x as a function of y. So I'm going to go ahead and x is equal to plus minus square root of y minus 1 to the third. Okay, because we're talking about the first quadrant, I'm only going to go with the positive value, y minus 1 to the third. If you recall your rational exponents, this can be also written as y minus 1 to the power 3/2. Now let's go ahead and do implicit differentiation. Turns out to be dx is equal to 3/2 y minus 1 to the power 3/2 minus 1 dy. So dx over dy is 3/2 y minus 1 to the power 3/2 minus 1 is 1/2. So that's my differentiation of x with respect to y. And when you have x is a function of y, the formula for the arc length, recall the formula for the arc length is equal to, the bounds will be the y values, y is equal to a to b square root 1 plus dx dy squared, operator dy. Let's plug the values in. Y is equal to a, which is 1, so from 1 to 5, these are my bounds, square root of 1 plus dx over dy squared, so which is 3/2 times y minus 1 to the power 1/2 squared dx. Okay, 1 to 5 square root 1 plus 9/4 times y minus 1 dy, because square and square root will cancel for the y minus 1, and 3 squared is 9, 2 squared is 4. Clean up a little, simplify a little. 1 to 5 square root 1 plus 9/4y minus 9/4 dy. Now we can subtract, we can do 1 minus 9/4. So 1 to 5, 1 minus 9/4 would turn out to be negative 9/4y minus 5/4 dy. Now I'm going to do, because the derivative of inside is just going to be 9/4, I can do use substitution to evaluate this integral. So I'm going to let 9/4y minus 5/4 as u. Okay, that would give me 9/4 dy. This is going to give me 9 over 4 dy is equal to du, which gives me dy is equal to 4 over 9 du. Okay, now I'm going to leave the bounds in terms of x's, in terms of x, because I will probably come back to x. X is equal to 1 to 5. I have 4 over 9 square root of u du is what I'm left with. Okay, so 4 over 9, x equals 1. So when I do the integral, this is going to turn out to be u to the power 1 half plus 1, which is 3 halves. And I will be dividing with 3 halves, which is same thing as multiplying with 2/3. Again, the bounds are x equals 1 to x equals 5. Now I'm going to go back. I'm sorry, these were the y's. I apologize. No x's here. These bounds were the y bounds. So not x bounds, these were the y bounds, okay? So y is equal to 1 to y is equal to 5. Here again, y is equal to 1 to y is equal to 5. The reason why I left the bounds in terms of y, because I'm going to come back in the y form now. So I'm going to replace the u by whatever we called u in the beginning. The bounds are 1 to 5. Okay, so go ahead and simplify. Either use a calculator, plug the upper bound and the lower bound. Check. It should turn out to be 9.073, approximately 9.073. Okay. All right, next example, we have find the arc length of graph of y is equal to natural log of cos x from x equal to 0 to x equals pi over 4. So here, we're given the graph of natural log of cosine of x, and we're looking for this curved length of this curve. Okay, y is given as a function of x, so it's really important for me to notice the formula for the arc length. It is going to be x equals a to x equals b square root of 1 plus f prime of x squared dx. Okay, let's see. So x equals a to b. See what I'm left with. Natural log of cos x from x equal to 0 to x equals pi over 4. Okay, so we're given y is equal to natural log of cosine x. Y prime would be 1 over cosine x times derivative of cosine x, which is negative sine x. So y prime is going to turn out to be negative tangent x. So when I plug the values into the formula for the arc length, I'm going to say arc length is equal to x equals a to b, which I'm going from 0 to pi over 4 square root of 1 plus f prime of x squared dx. Okay, from 0 to pi over 4 square root of 1 plus tangent square x dx, which turns out to be 0 to 4. 1 plus tan square x is secant square x, if you recall your trig identities. And square root and square will cancel. This is pi over 4. 0 to pi over 4 secant x dx. Integral of secant x is equal to natural log of secant x plus tangent x, going from the bounds from 0 to pi over 4. So we have natural log of secant pi over 4 plus tangent pi over 4 minus natural log of secant 0 plus tangent 0. Simplify using a calculator, it turns out to be square root of 2. It can be done without a calculator as well. Remember your special trig values, the acute angles, first quadrant, that is enough to come up with the whole unit circle special angles. Okay, so natural length of square root of 2, which is approximately equal to 0.881, and that is the arc length for us. Okay. All right, next example, let's check this one out. This was number 5. Here's number 6. Find the arc length. Again, we are given y as a function of x. So arc length formula would be x equals a to x equals b square root 1 plus f prime of x squared dx. Okay, this is y. Y is equal to x to the power 3 halves. I like it written in terms of an exponent. It's easier for me when I do the derivative or integration. And then y prime would be 3 halves. X to the power 3 halves minus 1. 3 halves minus 1 is 1 halves. Okay, so 3 halves minus 1 is 1 half, right? So y prime is that. Okay, so plug everything into the formula. Arc length turns out to be, the bounds are from 0 to 2. No need to graph the function. We only need to find the derivative and its square and plug it into the formula. So we have 3 halves x to the power 1 half squared dx, which turns out to be from 0 to 2, 1 plus 9 over 4x dx. Again, this is a simple u substitution problem, so I can let 1 plus 9 over 4x be the u, and that means 9 over 4 dx be du. That means dx be 4 over 9 du. Okay, 4 over 9 du. All right, see, what are we left with? We're going from, okay, the bounds. Let's think about when x is 0. So if I change the entire integral into the u integral, when x is 0, u would be equal to 1. So when x is 0, u would be 1 plus 9 over 4x. So u would be equal to 1. And when x is 2, u would be 1 plus 9 over 4 times 2, which is 1 plus 9 halves. And 1 plus 9 halves is 11 over 2, 11 halves. All right, here we are. So we have square root of u du 4 over 9, because dx was equal to 4/9 du. And 11 halves is my upper bound. Okay, 4 over 9, u to the power 1 half plus 1 is 3 halves. And we're going to divide with 3 halves, same thing as multiplying with 2, same thing as multiplying with 2/3. And the bounds are from 1 to 11 halves. Go ahead and plug the upper bound and the lower bound and use the calculator to evaluate. It should be approximately 3.53 as my my length of the curve should be approximately 3.53. Okay, there's 2 try me problems on the next page. Pause for a minute, give it a try, evaluate the arc lengths, and then come back, match, and check with me. Okay, so pause the video here and find the arc length. Y is a function of x, so arc length would be equal to x equals a to, nope. Arc length would be equal to x equals a to x equals b 1 plus f prime of x squared dx. Okay, so y is natural log of secant x. Y prime would be 1 over secant x. What's the derivative of secant x? Secant x tangent x. So y prime is equal to tangent x. Get ready to set up our integral for arc length. Comes out to be from 0 to pi over 4 square root of 1 plus y prime squared, which is tangent square x. 1 plus tan square x is secant square x. So square root of secant square x dx. Now that is going to leave me with 0 to pi over 4 secant x dx. Okay, what is integral of secant x? It is secant of It's natural log of secant x plus tangent x. So natural log of secant x plus tangent x going from 0 to pi over 4. Plug in the upper bound and the lower bound. So we would get natural log of secant pi over 4 plus tangent pi over 4 minus natural log of secant 0 plus tangent 0, plus the values of special, plug in the values of special acute angles, turns out to be natural log of plus 2 minus 1 minus natural log of 1. Natural log of 1 is equal to 0, so this piece is going to be gone. Natural log of 1 will not be there anymore, and we'll be just left with natural log of root 2 plus 1, absolute value of it. It's positive, no need to leave that, no need to put the absolute value bars. You can drop them, but I'm gonna leave it at this point. Go ahead and use a calculator, simplify if you want to. Okay. All right, next problem. Find the arc length of sine curve from x equals 0 to x equals pi. So this one says it needs numerical integration. I'm only going to set up the integral, okay? Set up the integral only. That means we are not able to use any integration techniques we have learned so far. We would have to rely on numerical integration, or for now you can use the integral calculator, a calculator that does definite integral for you. So y is equal to sine x, y prime is equal to cos x. So arc length would be equal to, from x equals 0 to pi, square root of 1 plus f prime of x. What is f prime of x? It's cos square x dx. Okay, and that, if you use an integral calculator, it's going to come out to be 3.82. We haven't talked about numerical integration yet, but for now you can use a calculator, or just there's tons of free calculators over the internet that you can find that will do symbolic integration for you. Okay, next example. Let's see. We have find the arc length of this curve f of x equals x squared over 2 minus natural log of x over 4 over 0 to 2. Okay, really quick. I'm writing arc length formula with every single problem so that you remember what arc length is equal to. X equal to a to x equal to b, 1 plus f prime of x squared dx. Okay, so f of x is given to me. F of x is x squared over 2 minus natural log of x over 4. What's f prime of x? Let's go ahead and take the derivative. Derivative would be x minus 2x over 2, which is x, minus 1 over 4x. And if I do f prime of x squared, then I have x minus 1/4 of x squared. That, if I FOIL, x squared plus 1 over 16x squared minus 1/2, if I FOIL this. Now let's plug it into the calculator. We have arc length equals from 2 to 4 square root of 1 plus f prime of x squared. We already did that piece. X squared plus 1 over 16x squared minus 1/2 dx. Okay, so going from 2 to 4, looks like there's like terms, 1 and negative half would be x squared plus 1/2 plus 1 over 16x squared dx. If you realize the inside is a perfect square, so this is from 2 to 4, I have a perfect square lying in here, which is x minus 1/4 of x squared dx. If you FOIL this, you should get this back. So recognize this as a perfect square. It's a perfect square trinomial. All right, so now square root and square can be cancelled, so we can get rid of the square root and the square, and all we are left with from 2 to 4, x minus 1/4 of x dx, which when we do the integration, it's x squared over 2, x squared over 2 minus, let's see, this is, let me do one more step before we get there. So we can write it as 2 to the 4th x minus 1/4 x to the power negative 1. Actually, it's okay to leave it as 1/4 x, because what is integral of 1 over x? So this is going to turn out to be integral of x is x squared over 2 minus 1/4 natural log of x, going from 2 to 4. So it turns out to be 4 squared, which is 16 over 2, minus 1/4 natural log of 4, minus 2 squared, which is 4 halves, plus 1/4 natural log of 2. If there's any like terms, combine them. 16 over 2 is 8. 8 minus 2 is 6. So this turns out to be 6. Negative 1/4 natural log of, let's see, what it be? Negative, when we subtract, it becomes positive. We'll do subtraction. Yeah, 1/4. So negative 1/4 natural log of 4 plus 1/4 natural log of 2. So we can do a little more manipulation here. Natural log of 4, can I write this as 1/4 natural log of 2 squared? So this would actually become negative 2/4 natural log of 2. So this can be written as negative 2/4 natural log of 2. So we have negative 2/4 natural log of 2 plus 1/4 natural log of 2. So that we can combine the like terms. It turns out to be 6 minus 1/4 natural log of 2. Okay, so this piece is what I had written. That would be our final answer, length of curve. It is very nice to plug in your answer as a rational form in case you have your homework on MyMathLab, because it understands the fractions rational form much better than it understands the decimals. Sometimes it's picky about the number of decimal places. All right, next example. Find the arc length of f of x. Again, we're given y as a function of x, and I'm going to plug them into the formula. Arc length is equal to x equals a to x equals b square root 1 plus y prime squared, or f of x squared, however you want to write it. Same thing. 1 plus f of x, f prime of x squared dx. Okay, so we are given f of x as 1/3 x squared plus 2 to the power 3 halves. It is time to find f prime of x for me. It's 1/3 times 3 halves x squared plus 2 to the power 3 halves minus 1. 3 halves minus 1 is 1/2, but I must multiply with the 2x because of the chain rule. So f prime of x, a little cleaned up form. 3 and 3 can cancel, 2 and 2 can cancel. I'm just left with x times x squared plus 2 to the power 1/2. Okay, plug it into the formula for the arc length. Arc length turns out to be from 0 to 1 square root 1 plus f prime of x squared. Okay, as you can see, when I open up the bag, when I square, I would be able to write x squared times x squared plus 2, because a 1/2 and 2 will cancel each other. Square root and square will cancel there. So 0 to 1, 1 plus x to the 4th, if I distribute the x squared inside, plus 2x squared. Okay. And again, if you realize or recognize it, it is a perfect square, which is x squared plus 1 squared. So if you FOIL x squared plus 1 squared, you do get this. If you FOIL this expression, you get this expression inside the square root. Okay, and that turns out to be square root and square can be cancelled now. So 0 to 1, x squared plus 1 dx. Now that integral is a piece of cake because we can just evaluate the integral of two pieces going from 0 to 1. 1 to the third power is just 1. So I'm ready to plug the bounds in. 1 to the third power is just 1 to the third plus 1 minus 0 over 3, which is 0. So that is going to equal 4/3. And that's my arc length. 4/3 is the arc length in this case. All right, couple more examples. Only 2 more left for the arc length. All right, so let's check out number 8 next. Your integration technique, your integration has to be profound in order to solve these problems because you should know all your techniques of evaluating basic integrals. Here's number 8. Find the arc length y is equal to square root of x minus x squared plus sine inverse square root of x over 0 to 1. Okay, so again, y is a function of x. So my arc length formula is going to be x equals a to x equals b square root f prime of x squared dx. All right, so y prime, y is given to me. Y prime, let's just write down the y one more time, and then we can do y prime. So y is equal to x minus x squared to the power 1/2 plus sine inverse x to the power 1/2. When we do the derivative, we would have to use the chain rule, so make sure you're not rusty on your chain rule. 1 over 2 square root of x minus x squared. It must be multiplied with the derivative of the inside function. Integral of sine inverse x is 1 minus square root of x squared would be just x, and it must be multiplied with the derivative of the inner function because of the chain rule. Okay, clean up the y prime a little bit. It turns out to be 1 minus 2x over 2 square root of x minus x squared plus 1 over 2 square root of 1 minus x, and then we have x to the power 1/2 here. Notice the fraction here, I can write it as 1 minus 2x over 2 root x. I can pull out an x from this root and I would have 1 minus x in there. One on the top I have x to the power 1/2, 2 root 1 minus x. Now I'm very close to getting the common denominator, so I'm going to write it as a common denominator. The reason why I'm doing this is when I plug it back in, simplification would become a little bit easier for me. Okay. So the common denominator here turns out to be 2 root x root 1 minus x. The first fraction does not need to be multiplied with anything, but the second fraction does need to be multiplied top and bottom with the root x, okay, to get the common denominator. So I have 1 minus 2x plus x to the power 1/2 times x to the power 1/2 is just x. That turns out to be 1 minus x on the top, 2 root x root 1 minus x. If you recall, algebraic simplification, 1 minus x can be written as square root of 1 minus x times square root of 1 minus x divided by 2 root x times root 1 minus x. Because if you multiply root 1 minus x times root 1 minus x, you will get your root, just 1 minus x back. Okay, the benefit of doing this was I can get rid of one of these, and my y prime is much cleaner now, 2 root x. Now let's go ahead and plug it into the formula for the arc length. So we have arc length is equal to, our bounds are given over 0 to 1, 0 to 1, square root 1 plus y prime squared. So my y prime is going to be, let's see, so 1 minus 2x. Let's double check my work here. 2 1 minus 2x, that's 1 minus x. Okay, x minus x squared to the power 1/2, that looks all good. 1 minus 2x plus x over 2 root x. So that would be 1 minus 2x. We did not have to multiply anything with the first fraction. Okay, so that turns out to be, there's a 1/4 over here. I'm going to do a little bit check up here, check my derivative portion one more time. So clean up this page, and I'm gonna do the integral one more time. Double check. Looks like I made a small, I'm missing a 2 somewhere, looks like to me. Maybe I'm not, so I'll find out. Let's check it out one more time. Okay. All right, so I did write it in terms of x minus x squared to the power 1/2. That is perfect. And sine inverse x to the power square root of x, that's perfect. When I do y prime, it's 1 over 2 square root of x minus x squared times 1 minus 2x plus 1 over square root of 1 minus x over 2 x to the power 1 negative 1/2, which is square root of x. So y prime at this point is 1 over 2 square root of x minus x squared. And on the top, we have 1 minus 2x. The second fraction, we have 1 over 2 root x root 1 minus x. Okay, cool. Looks good. And now we can pull out an x from this square root. So it's in the numerator, I have 1 minus 2x over 2 root x root 1 minus x. That all looks good. Now plus 1 over 2 root x root 1 minus x. Okay, I see. All right. So now, yep, there was a small error somewhere there in combining the fractions. So now my common denominator here turns out to be 2 root x root 1 minus x. And the numerator, I can combine the like terms, turns out to be 1 minus 2x plus 1, which turns out to be 2 minus 2x over 2 root x root 1 minus x. If I pull a 2 out from the top, I can cancel the 2 at the top and at the bottom. Now remember or notice, this is something from algebra. I'm just using a little technique here from algebra. 1 minus x is equal to root 1 minus x times root 1 minus x, because root 5 times root 5 is equal to root 5. So that's exactly what I'm using over here in terms of the variables. So I'm going to break the numerator. My fraction would become root 1 minus x times root 1 minus x divided by root x times root 1 minus x. I am able to cancel one of these between top and bottom, root 1 minus x over root x. If you want, you can write it all together all at once. Good. So that's my y prime. So at this point, I have my y prime as 1 minus x over x, square root of the whole thing. Let's go ahead and set up our integral. Our bounds are from 0 to 1. So arc length is going to be from 0 to 1. And square root of 1 plus y prime squared, 1 plus y prime squared dx, which is going to be 0 to 1 square root 1 plus 1 minus x over x squared dx. Now square root and square will actually cancel each other there. So I have 1 plus 1 minus x over x dx. Let us see what can I do with this integral here. So from 0 to 1, let's get the common fraction, common denominator here. So I'm going to multiply top and bottom and then x here. So I have square root x plus 1 minus x over x dx, which is 0 to 1. Looks like I can get rid of the x and x, which is just square root of 1 over x dx. Now we know how to evaluate integral from 0 to 1 x to the power negative 1/2 dx. That's what I'm looking at. And integral for x to the power negative 1/2 is we're going to add the exponent. We're going to add 1 to the exponent. Negative 1/2 plus 1 is positive 1/2. And divide with the new exponent, which is going to be dividing with the half, same thing as multiplying with the 2, going from 0 to 1. So it turns out to be 2 times 1 square root of 1 minus 2 times 0. So my final answer turns out to be 2. The arc length is 2 in this case. So for the given function, the arc length is 2. Okay. One more example. Here we are given x is a function of y. When x is a function of y, remember the formula for my arc length is y is equal to a to y is equal to b square root 1 plus dx over dy squared dy. So we have to use implicit differentiation in this case, and that should turn out to be, let's see, I can say x is equal to 1/8 y to the 4th plus 1/4 y to the power negative 2. The reason why I wrote it in terms of exponents, it's easier when we do derivative and integrals when we're dealing with the exponents as compared to the denominator if we had y squared in the denominator. Okay, so dx over dy, the integration of this function, differentiation of x with respect to y turns out to be 1/8 times 4 y to the 3rd plus 1/4 times negative 2 y to the power negative 3. Simplify it a little bit, it turns out to be 1/2 y to the 3rd minus 1/2 y to the power negative 3. Okay, 1/2 y to the 3rd. I can pull out a 1/2 just because it's probably nicer to do so. There we go. That's our x dx dy, or we can say x prime, derivative of x with respect to y. Now I'm ready to set up the arc length. So I'm going to say arc length is going to be from 1 to 2. These are going to be our y bounds. We'll check that in a minute. So just say these are y bounds given. These are y bounds given. Okay. Let's just assume that we are given the y bounds. So arc length is from 1 to 2 square root of 1 plus y prime squared dy. X prime dx dy squared. Okay, so I got to take care of the square root over there. So I have 1 to 2 square root of 1 plus 1/4, and this would become y to the 6th power plus y to the negative 6th power. I'm just foiling y cubed minus y to the negative 3rd minus 2 times y cubed times, so that would be minus 2. Okay, let's distribute the 1/4 inside and see if there's any like terms that I can combine. Going from 1 to 2, we have 1 plus 1/4 y to the 6th plus 1/4 y to the negative 6, and then minus 1/2. There are like terms we can combine. 1 and negative 1/2 can be combined. So going from 1 to 2 at the square root, 1/4 y to the 6th plus 1/4 y to the power negative 6. 1 minus half is a positive 1/2 dy. Do not forget dy. Okay, let us see. Is there anything I can pull out of this? I can pull out a 1/4 from here. So between 1 to 2 square root, pull out a 1/4. That leaves me with y to the 6th plus y to the negative 6. If I want to pull a 4th out from here, then I have a plus 2 here dy. Getting the 1/4 out of the square root, I would have a 1/2 out, and inside y6 plus y to the negative 6 plus 2 dy. And I do have a perfect square inside now. If I FOIL y to the third plus y to the negative third, if I square this, I would get this if I square this. Okay, so I do have a perfect square. Now again, the square and the square root are going to cancel each other. So I'm left with 1/2 going from 1 to 2, y to the third plus y to the negative third dy. This integral is not too difficult. We can just do integral of pieces. So 1/2 y to the 4th over 4, and this would be y to the power negative 3 plus 1 is negative 2, and we're also going to divide with negative 2. Divide with negative 2. So that would be negative 1/2 y to the power negative 2. And the bounds are from 1 to 2. Okay, so let's see, 1/2 y to the 4th over 4 minus 1 over 2y squared. The bounds are 1 to 2. Let's go ahead and plug the bounds in. 1/2 sticks around in the front. Y to the 4th is 2 to the 4th power. 2 to the 4th power is 16 over 4 minus 1 over 2 times 2 squared is 4 minus 1/4 plus, because I'm going to distribute the minus in the second parentheses when I plug in the lower bound, it would be 1 over 2. Okay, some combine, simplify the fractions. It's going to be 33 over 16. Okay, let's check it out, double check my work. Okay, that's all the examples for arc length.